Good afternoon, everyone. We're going to start up again, so please take your seats. We're carrying on with the CPUE topic, and so Laura's going to give the comment, and then we're going to go into discussions. Okay, great. Whenever you're ready.
Okay. What should I? Oh, okay. So what should I do?
I don't know. I'll change it.
Okay, thanks. Okay. Thank you. Thanks, Mark, for the introduction, and thank you to Nicolas and Toshi for an excellent talk. So this is my comment on the CPU standardization session. My name is Laura Tremblay-Boyer, and I'm a fisheries scientist with CSIRO. One of the points that Nicolas made during his presentation was that with the advent of spatiotemporal models, we've been forced to think a lot more about what we want to define as a catchability or a density covariate. And that's something that we've always had to do in the past when we do CPU standardization, because we're trying to remove the effects of catchability, of changing catchability over time from our catch and infer data. But we've been thinking a bit more about it now that we're using spatiotemporal effects. And it's kind of at the core of CPU standardization. And that's because when we standardize CPUE, we're not undertaking a typical modeling problem. What we're modeling is CPUE as a function of the data matrix X, and the model matrix beta. And we're modeling our observed variable, but really what we care about is the model matrix and how it breaks down the effects of catchability and density, because that's what we're going to use to build our index of abundance. So CPU standardization is all about our model matrix beta is built, but we're dealing with fishery-dependent catch and infer data. So that's essentially an uncontrolled natural experiment where we have unbalanced observations along our covariates. And so the effects that are of the covariates that we're interested in our model matrix, they're often not actually separable by the model. So in the perfect world, we'd have this ideal experiment where we've sampled the covariates we're interested in across both axes. And so we're giving power to our model to split the effect of one versus the other. But in practice, that's not what we have. And this problem is compounded by the fact that GLMs, GAMs, and expansions thereof, they're all modeling frameworks that are optimized for prediction and not inference. And inference is what we need when we're building our model matrix. So just to give you an example of account for the catchability and density covariates. So one frequent density covariate that we think about is SST, and another covariate, a catchability one would be skipper experience. So if we're, for instance, trying to standardize our CPUE to account for changes in SST throughout our fishing grounds and remove the effects of the vessel effect from our observed CPUE, in a control experiment, we would have had all the vessels with a range of skipper experience, sample evenly all SST conditions across seasons. And so our model would have enough information to separate the effect of SST versus skipper experience on observed catch and effort data. But in reality, we will often have specific vessels that are only active in certain areas or months. And it's going to be hard for a modeling framework to separate those two effects. So is the higher CPUE due to the vessel effect or to the SST effect? And this is further compounded by the fact that the tools that we use for model selection, they tend to focus on prediction. even when those metrics try to penalize for complexity, in practice, often the models that get chosen at the end tends to be one of the most complex ones that explain the most variability in the data. And that's often one of the first questions that you get from newcomers to CPU standardization is, how do I know which one is the best model? And I'm always, I always freeze a bit when I get that question because I don't have a ready answer for them. I think a lot of people still argue, and depending on where you are and which country you're in, you're going to use a different method for model selection. There's a lot of people, or there's a few places where automated model selection is what's used. And there is a case to make for that because it's convenient and it's easy. You can churn out your indices fairly quickly. You can get an experienced analyst to do your model selection. But often when you use automated model selection, you will remove covariates that might be actually very important to your fishery if they're not introduced in the right order. Or you could conversely retain some spurious effects. And these are all flaws that are well demonstrated in the ecology literature, but we don't really talk about it in the fisheries science. So I've included here a paper from the ecology literature that discusses this, but I do find it useful to look at how ecologists go about understanding prediction versus inference. You do have to take a few extra steps to apply it to the type of work that we do, but it's still an interesting framework and good things to always keep reminding ourselves about. So of course, we are still dealing with natural experiments. And so it's always going to be hard to optimize for inference without independent balanced data, and we don't have that. So spatial temporal models have become more popular in recent years. And they're a lot more powerful way of accounting for spatial temporal effects. So it used to be that we would attempt to deal with those effects with categorical effects like areas and grid cells, and eventually we started using surfaces and gaps, and now we're able to use Gaussian random fills. And those models do a great job at imputing and at treating missing cells in some instances. As something discussed with Nicolas, there are caveats there. But the spatial surface is still a proxy for unmodeled spatial effects. But those spatial effects do end up being treated as a density covariate. So if you have some unmodeled catchability effects in your system that have a spatial component and are not part of your final model structure, it could still get included in your spatial effect and treated implicitly as a density covariate. You also need to be cautious about the introduction of complicated spatial-temporal interactions. So that's true for GAMS and for VAST. Because again, it's hard to control how much of the interaction captures density versus fleet behavior. And again, one of the big examples here is that often you have seasonal fleets that are only fishing in specific areas. And so it's quite hard to separate the two effects. You can explain more of the data with a flexible spatial-temporal interaction, but it's unclear whether what we're explaining is actually a density or a catchability effect. So you do have to be cautious when you use those types of surfaces. So another place where we have run into the risk of confounding catchability and density covariate is when we describe targeting clusters based on species proportions. So targeting clusters are often used as a catchability covariate in CPUE standardization for mixed species fisheries. So that's what most tuna fisheries are. And they often end up being influential covariates because they're changing through time, and they affect CPUE because by definition, they're often defined from species proportions. So they do have an effect on CPUE. But when you only use species proportions to inform your targeting clusters using an unsupervised classification algorithm, it's unclear whether you have a species proportion that is higher because the species is targeted or because it happens to be more available at that area and or time. And so this is not an issue for all species. So you have some species that have very specific types of gear types or targeting, like southern bluefin or swordfish in some fisheries. And so in those instances, it might be okay to only use species proportion as a proxy for targeting. But so For some other fisheries, you might need to actually expand your model to look at other covariates to really get a good picture of how targeting is changing through time. And a really useful exercise to do in those instances is also to consult with the stakeholders from the fishing industry, because they'll have actual on-the-ground knowledge of what they're trying to target, even if it hasn't been recorded in the logbooks. So one example here, I'll walk you through this one, is from the Eastern Tuna billfish fishery in Australia. So we know from talking to the fishery stakeholders there that the fishing strategies have changed a lot through time. And we also were aware that they had a few different ways of catching different types of the target species. So instead of having a cluster algorithm run over the whole period of the data that we were trying to index, so that's 1998 to 2021, we instead built a clustering algorithm that includes species proportion, but also gear effects. So I'm thinking the length of the main line, the number of hooks, whether there was lights usage, that type of side effects. And we ran the clustering algorithm separately for each year. And we asked, we had a little play with it, but we asked for 6 clusters to be outputted from this algorithm. So each of those points here on the graph is one of the 6 clusters for each of the year. And they are colored as a function of the species that was the most caught in the clusters. So green is albacore, this light blue here is swordfish, yellow is yellowfin, and red is southern bluefin tuna. And what came out, and this is called a force-directed graph, and what it does is that it visualizes the distance between each of the clusters. So we used that because we wanted to see if we'd be able to identify fishing strategies that were constant through time versus fishing strategies that were evolving. And when we did that, we identified that there was actually 2 different fishing strategies for yellowfin and the ETBF that are quite different. So you can see that you've got a cloud of yellow points here and a cloud of yellow points here. And we also had 2 very different strategies fishing for albacore throughout our time series. So there's no easy fix if you have your confounded density and catchability covariates, because we can only deal with the data that we have, but we can at least be cautious about the covariates that we use and the models that we select. So one thing we could do is we can avoid automated model selection and prediction-only performance metrics and come up with a list of reasonable model structures based on domain knowledge. We should also examine individual fitted relationships, not just overall predictions, and most definitely go beyond residual diagnostics, which by definition only focus on predictions. So inference and stepwise plots and predicted relationships between CPUE and each of the covariates are really useful additional tools to look at to make sure that our model makes sense. And you should focus on getting to know your system and using domain knowledge. So going beyond the literature and engaging with fishers. Avoid black box presentations to stakeholders where all you show is your nominal and your final index and a histogram with your residuals, because they're not going to be able to provide feedback, useful feedback on whether your model is passing the red phase test. And in some instances, you can identify key knowledge holders and engage directly with them. So as an example, next week, we were having, with the ETBF, we're having a stakeholder meeting, and we've asked the fishing industry to ask 3 of their most skilled skippers, and they're going to come and meet with us for a few hours, and we're going to run through some of our targeting results with them. And so that's going to be a one-on-one interaction, keeping it informal. And so we're hoping that we'll be able to gather additional information to fine-tune our classification algorithm from those meetings. Obviously, this is a tricky one with tuna RFMOs because we're often quite far removed from the fishing industry because of the way the system is, but also sometimes because of the culture and the language. But it is a worthwhile effort if we're able to undertake it. And I will stop here because I am over time, but I'm happy to discuss further other places where we have confounded catchability and density covariate.
Yeah, thanks, Laura. Any questions for Laura on her presentation? Carolina, you? Yeah.
What Laura was saying of interviewing the skippers and talking to the industry is very interesting. And I wonder if we should, like as a group, maybe commit into like cataloging changes in the industry and sort of have a group, let's say, understanding of what's going on, because some of the fleets are shared among oceans, and there's changes like in technology or in service that they are hired to help them like identify oceanographic patterns, etc. And also changes in the actual recording of the data, like electronic logbooks and I don't know, capacity building for them to fill them in a more accurate way, etc. So I think might be a good time for us to kind of agree that we should start cataloging these changes to help us even understand these trends, right?
Yeah, thanks. Simon, you have a comment?
Yeah, I just wanted to agree with Carolina that that kind of long-term history of changes in the fisheries, all of the different fleets that are included in these indices is really important, that kind of background knowledge. At IATTC, used to have visiting Japanese scientists coming in, documenting all of the changes in the Japanese fishery roughly once a decade. And those documents are really super valuable for understanding what happened in that really important time series. So maybe that's something that should be expanded to other fleets as well.
Yeah, something that was interesting that came from one of our recent meetings was that the fishing industry named 5 vessels that had explicitly changed strategies from targeting sportfish to albacore. And so we were able to track back what those vessels were in our database. And it's just kind of interesting side information because it allows you to ground truth, is my classification algorithm picking up that those vessels have changed strategies, or is it just getting mumbled with the other clusters that I have? So you can actually get useful information to take another look at your model using a different type of data. I mean, it's not formal data, but it's still quite useful data in that context.
Anything else? Yeah, Icon.
Hi, Laura. Thank you for your presentation. Yeah, you mentioned about model selection, and I have one question about model data issue. So I think one thing I haven't seen we talk a lot in the CPUE standardization is that we haven't compared model with and without the temporal correlation in the spatial-temporal term. And in one situation, in the EPO, we found assuming independent spatial-temporal component between year and adding the correlation can make a big difference in the results. And I don't know whether you have some experience with comparing model with and without considering temporal correlation for the spatial-temporal term in the spatial-temporal model. Thank you.
So thanks for that comment. That's an important point. Do you recall what was the difference that you were observing between your 2 models?
Yes. So the case study is for big eye tuna in the Eastern Pacific Ocean, and the problem with that data set is that there's a local depletion occurring, and due to likely preferential sampling, the fish remove out of the region with depleted stock. So we need the model, the spatial-temporal model, need to fill in the depleted area. And if we only use the spatial term, if we only use spatial correlation to do the imputation, like Nicholas mentioned, it tend to regress to the mean. So it tend to overestimate the abundance in the depleted area. So, and we did some simulation by looking at whether adding temporal correlation makes a difference, and we found it did, and the result shows that using data in nearby year for the same location can be more informative than using the data from far locations within the year. I don't know whether I explained that clearly or not, but yeah, that is the case we have.
Yeah, so I guess that's what Nicola was referring to in his previous presentation, that when we're using the spatiotemporal models, if we're lacking information for some of our strata, there's sometimes going to be imputation behavior that it's a bit cryptic and we're not necessarily aware of. And I think, I can't think of a model selection tool that's bespoke for that specific issue, but I do think that when you're doing these types of imputations, you do have to look at the fine scale predictions that your model is producing. Especially for spatiotemporal models, because this way you'll be able to pinpoint when you have certain spatial strata or spatiotemporal strata that are reverting back to values that are not really making sense from your understanding of the system.
Yeah, thanks, Laura. I think we'll move on to general discussions, but again, you can ask questions to Laura and to Toshi and to Nicola. But Nicola, you have a question?
Follow up on the same topic. I think Laura covered it really well. Kind of just off the top of my head, in those situations, I think it's interesting to look at the spatial residuals that you get from the models with and without, but also what the spatial temporal random effects are estimated at, and seeing if there's perhaps a disconnect or maybe a strong pattern in a strong pattern in either one that might be an indication that, I guess, a strong pattern in your spatial random effects is a signal that there's something about the abundance that's being modeled that you've not explicitly accounted for. Yeah, I don't know where I'm going with that thought. So maybe it just needs to be stricken from the record, but yeah.
Yeah, Charles.
Thanks, Laura, for the presentation. So I've just got an idea that I wanted to sort of put to the floor for discussion, really, and that's whether or not we're using our abilities to model CPUE data hierarchically, and whether we're using our sort of full potential, really, because you could conceive of a CPUE model where the catch rate is simply a function of the catchability and the density, and then the density is a function of something else, and the catchability is a function of something else, and you end up with this sort of hierarchical structure where it's actually explicit from the outset what you're modeling. We've been sort of experimenting with this sort of approach in New Zealand, where we're basically filling the catch rate data with just two parameters, which is the catchability and the biomass density, and then we make the biomass density a function of things like latitude or depth or so forth, and it seems to be reasonably promising. I don't know if it necessarily solves the problem of separability between the catchability and density effects, but it definitely makes it more intuitive, the process of developing the model. And I just wanted to sort of put that forward as a possible avenue for future investigation.
Yeah, thanks, Charles. I think that highlights something that's important. Like 30 years ago when I started doing stock assessment, like everybody else, your first job is to do a CPU standardization. You didn't even consider density versus catchability. You just assumed that the year effect was the population size and everything else was catchability. But I think we've moved towards what you're saying, and I think VAST basically does the same thing by forcing you to choose what's density and what's catchability. And I think that's where you're coming from too, because of the way you've modeled it. It's forcing you to choose which is which. And I think that's one of the biggest developments in CPUE standardization, since I started, is actually forcing you to do that.
So from what I understand, VAST is not hierarchical though. It still has everything in and it actually has things that could conceivably be density effects and catchability effects in both parts of the model. So in that sense, I haven't found it very intuitive to actually separate those things out and diagnose it properly. And one of the tricky bits is to get one density input and fit it into both model parts. And I'm not sure if VAST is able to do that yet.
Any comments on that topic, or if not, anything else? Oh, we have Dan Ovando. You have a comment?
Yeah, hi everybody. Tuning in from La Jolla. Great talk, Laura. I think this just speaks to, there's a lot of solutions in theory to model selection, but there's also, I think this speaks to a need for us to just think carefully about where the sources of information in our data are, right? And what I mean by that is, we can, I think it's a good thing for us to sit down and write down whether we're attributing a given variable to catchability or density. But at some point, some of those things are just not going to be separable without an experiment. This is really a causal inference question, right? If you throw, what is the effect of left leg height and left leg length and right leg length on height into a model, right? It's going to come out that, well, neither one's that important since it can't separate the two. And so similarly, right, working with some small scale fisheries in Peru, what we'd often see is they really wanted to put El Nino into the model, but without a clear model as to, well, is that a catchability effect or a density effect, right? And, you can definitely tell a story where it can go either way. So I think, going back to, Laura's point, I think it behooves us to really think about this in a causal inference sense and, with directed acyclic graphs and the like, and try and actually, map out what we think the causal links are and, think about, are there ways to actually test that, and where there's not, think about what the implications of that are, since often, not including something is kind of implicitly including it in some way. But I think this is a big issue that, we haven't thought about all that much, and that, like Laura was saying, we tend to focus on these kind of very predictive based model things when really it's a causal inference question, which we're not that well set up to answer.
Yeah, thanks, Dan. Any comments or questions? Yeah.
Thanks, Dan, for that comment, and thanks for bringing up experiments. It's not really a tool that we've used for CPU standardization so far, but it does seem like something that we should be considering in order to splitting those density versus catchability effects. So one of the points I made on one of my slides, but I don't think I said it explicitly because I was rushing, is, and I've actually never done that for fisheries data, but I have done it for ecological data looking at mercury concentration and fish muscle, is that if you have an understanding of how a covariate is expected to be acting on either density or catchability, and you might have that information from a separate experiment that you did with fishers or interviews, pick your data source, but let's say it's independent from your fishery dependent data set, you could consider fixing the relationship as part of your model, and then using the residuals from that relationship as your basis for CPU standardization. I'm not sure if this is a good idea to explore, but when I was preparing for this presentation, I was feeling quite frustrated that I didn't have any solutions to propose except for, make sure you know your stuff and don't, just walk into your model and spit something out and then move on. And so that was one of the things I did think might be something worth exploring. Not that I'm going to go and do an experiment anytime soon because I'm terrible on the field, but maybe other people more suited could consider that option.
Yeah, I think that's a great point. If I understood you correct, you're kind of describing instrumental variables essentially. I guess what along those lines, what I would along with the ecological literature on this, this is essentially the field of econometrics, right? This is causal inference in natural systems when we don't have experiments. And I think, along with, like you're saying, going out and seeing, can we do actual experiments and use that, thinking about how as a field, between all of us, do we have some interesting natural experiments on this kind of thing that might help us kind of do a better job of teasing this stuff out and kind of learning from different systems there. So yeah, that's a great point. I would definitely, folks are interested, point folks to the econometrics literature, since basically that's exactly what this whole problem is.
Okay. Thanks, Dan and Laura. Any other topics people want to bring up? Okay. Oh, Carolina.
So in the Atlantic, I know there was a simulation experiment done for producing long line data and given to several analysts to analyze. And I wonder if that kind of exercise might help us here to learn a little bit what should we do and what should we not do.
Anyone want to comment on that? Yeah, Nicola.
Yeah, I think there's always a lot of stuff that we can learn from simulation, and I don't know, maybe there already has been a simulation done on this, or someone's already working on it, but the implications of putting in the catchability or the density covariate wrong under different patterns of different abundance distributions, but also different sampling patterns. I mean, I think you can learn some things from that, but there's also going to be a fair amount of case-by-case basis, just depending on the nature of the relationship and how much you can mess things up by getting it wrong. Because we're not likely to know what it is. Well, we might not know which is the right way to do it. I think it's probably important to explore using it in both ways if you do think it's strongly confounded, and then really interrogate the results and see if either one of them appears to be supported by independent sources of information from other studies or other background knowledge, to see if you can't identify which one is more plausible that way.
Yeah, Simon.
Yeah, I'd just like to agree about simulation experiments being a really good way to, well, really important in any kind of CPUE standardization. Basically, it's in any big CPUE, big important CPUE standardization, I think simulation is vital. There are lots of different things to test, and simulation is usually the best way to test them. As for going to larger experiments where you generate data and send it out to multiple different groups, having just done that with the spatial simulation experiment, I can tell you it's a lot of work, and I think it's a good idea, but I guess it depends on case by case how much benefit there is.
Okay. Thanks, Simon. Any other questions? If not, I'd like to move on to targeting. So Toshi, in his presentation, looked at targeting and did clustering analysis of species comps to find clusters, and then use that to, I guess, identify targeting in terms of clusters. But his results showed that just using the one cluster that was supposedly targeting didn't do as well as including all the clusters, because there was a bit more variability. I'm not sure if that was seasonal or just because of the low sample size. But then Simon's done some work, well, that was on targeting similar approaches though. So is there a sort of a general approach that people are now thinking is the best way to go forward, or is there still a lot more research to be done? What's the sort of the state of the art in determining targeting?
I don't know what the best option is. I mean, none of them really work all that well. and there's definitely room for improvement and better methods to be developed. I mean, one of the issues that I think Toshi raised and Laura raised was about confounding between different species. If you have, for example, targeting that is for big eye or yellowfin, and actually they're not targeting big eye or yellowfin, they're targeting both big eye and yellowfin. And so if you're using the two species in your standardization as potentially separate targets, then you're likely to pick up abundance variation rather than targeting, and that's what you don't want to do. So that's a bit of a problem for a standardization, for a clustering or a standardization that's covering the whole spatial domain. What we did when doing separate analyses by region was to, in the temperate areas where there's clear differentiation targeting swordfish or albacore or southern bluefin tuna versus big eye and yellowfin, to use clustering in those temperate areas. But in the tropical areas where most people are targeting big eye and yellowfin, most vessels are, then not to use targeting, but to use gear effects only. At that stage, we didn't have approaches that would let us combine gear effects and species composition, which is actually doing that is probably a better approach, to include the gear covariates as well. Another option for those tropical areas is to, rather than defining big eye plus yellowfin separately, just use the species composition of the combined big eye and yellowfin in your clustering, and then you don't split those two out as separate clusters. We didn't have time to do we haven't done simulation of that. I don't know what's the best option, and I think there's room for simulation to explore those issues.
Thanks, Simon. Toshi?
Thank you. Thank you, Mark, for raising this point. And like in Simon, I have no equivocal conclusion regarding which strategy is good or not. And in our case, we compare the result of using all the clusters and also one clusters, single clusters. And when we see the plot of the inference plot, which tell us that which categories or cluster influence to the temporal effect or not. So that is not the automatic criterion for the judging if you choosing one or either, but that may be useful for seeing the influence plot. And if the two clusters equally contribute to the temporal effect, we may choose. But one may be no impact or little impact, we may be removed. So that might be the approach. Yes. And also, I think Laura did a good job for raising another important point for that. She said the clustering is unsupervised learning. So we need some process for the validation, even a small portion of the data. So that'd be great. So the interview is costly, but I think that's great process for the make the result more persuasive. And also we did clustering through only the species composition. And there might be some circular argument that, as Laura mentioned, that the high proportion of the one species might be not the targeting, rather just accidentally or some high density in that point. So relying on only species composition may have a problem in some situation. So I think we may be able to do some clustering with the extra or auxiliary information, like a Fuchs between float and species composition together. And then normal clustering approach doesn't work. So another approach is to use some kind of the mixture approach. So that might be a kind of the model-based clustering. That may be the area for the future work. Thank you.
Thanks, Toshi. Any other comments on that, or any other points? Yeah.
Thanks, Simon and Toshi, for your comments about targeting and approaches to describe it. And I'm just going to go back to our fishing industry example, but one habit that we have when we show our clustering results is that often we'll just show the breakdown of what proportions of species are present in the clusters that we've identified. But I think it's quite useful to also map where the clusters are happening and also when they are happening and the distribution of gear settings for each of the clusters. And that's actually something that we've put together. I had a slide on this, but I skipped over it. But it's actually been quite handy because we were able to show the fishing representatives a summary of each of our cluster results in terms of species proportion, yes, but also where, when, and how they were fishing. And they looked at it, and some of them, they were like, yep, yep. And others are like, no, we weren't going after albacore in this one, we were going for yellowfin. And so that's all very useful information. And because we presented it using covariates that make sense to them, so the location, a map, when in the year, etc., they were actually quite keen to engage with us on that particular matter, and it's been quite productive for us.
Thanks, Toshi.
Thank you. I forgot to say, I had a great conversation with Haikun during the lunch break, and his question is our data is the 10 days unit, and so for each 10 days for each vessel will be allocated cluster 1 or 2 or 3 or 4, and if such allocation changes every 10 days, which means our clustering might be some misleading because that is just random changes, not a strategic. But if the allocation is very much continuously, like 2 months or 3 months in this cluster, and shift to the other cluster and continue, that might be some strategy. So that's kind of the checking or might be also useful for the future work. Thank you.
Okay, so related to that, to change their targeting, do the longline vessels have to change their gear? And does it take a significant amount of time, or is it simply a matter of changing the length of the buoy line or something like that? So how difficult is it for a longline vessel to change its targeting?
So that may not be a good question for me, and so my Japanese colleague may help.
Yes, in my experience in EPO analysis, there is no much great changes of the fishing gear during their fishing activities because, but we can find some signals for the differences of gear configurations between the oceanographic condition and the gear configuration and the oceanographic condition. That's it.
Thanks. Nicola, you have a question?
I was just going to ask Laura if she was going to talk about the example that she shared with me in a discussion yesterday about setting in relation to eddies. Because from what I understood, the gear configuration wasn't changing in that example.
Okay, yeah, so that's an interesting example I was going to bring up. Just again, going back to my fishing industry consultation point. So this is about the inclusion of eddies as what I initially thought was going to be a density covariate, but upon consulting with the fishing industry, they reported that not only they use eddies to help where they're going to do their fishing, but another thing that they do is that they will orient their sets, their long line sets, either perpendicular to the eddy, going from the edge to the core, or along the edge of the eddy if they're trying to either, and the perpendicular side is for catching multiple types of species if they're after byproduct species on top of their main target species, and setting parallel to the eddy is when they're only trying to focus on one type of species. So that was something I hadn't thought about and made me think, oh, hang on, maybe now I'm gonna have to, come up with multiple ways to describe the eddy location in order to capture what appears to be a catchability covariate as a function of the angle of the fishing set compared to the eddy. But then, you could, depending on how you think about it, it could also be density. So I still haven't made up my mind about that one, but it was definitely a very instructive outcome of the conversation that we had with the fishing industry. I have a question. Oh.
This is really interesting. I really agree with you that we need to have a better connection with industry, and you know what it's like out in Noumea, a long way from the centre of the purse seine fishery, and we never see them. I've never spoken to a skipper in 3 years, so I find this really difficult when we're looking at these data sets. One thing I know that I saw a presentation from the Global Fish Watch people the other day, and they have these amazing real-time trajectories of fishing vessels, and you can see how they're setting and at really high resolution. And I'm wondering whether that data source is something that AIS VMS type information is something that we can use a bit more in relation to understanding targeting practices, because we can get the catch data as well, perhaps for those vessels, and look at those behaviors that way. Just because I find it hard to get industry connection.
Yeah, no, that's a good idea. I have no clue how I'm presumably AI and maybe ChatGPT could make this for us. But I do think there are some people that are developing AI algorithms to extract the catch information from the vessels. I mean, I guess we'll have to see how good they are. I had a question for the group based on one of the points of Nicola's presentation. So I think we're all aware that preferential sampling is where CPU standardization is going to have to go. And we've been talking about that for quite a while now. I think since the early 2000s, where there was a Folly of Fantasy paper by Dr. Walters, and it keeps coming up, but we still don't include it in CPU standardization. And I was just wondering if there's any of us amongst the group that has had some actual experience working with professional sampling models with catch and infer data, or thinking about how they would go and incorporate it in CPU standardization.
I guess that's something that people better start doing then. I think Jim Thorson has done a little bit on that. I'm not exactly sure what he does or how he does it, but I think it's part of it. Okay, any other questions or comments? I'm sure there is something. Let me just check my... So I guess going back to the Toshi's talk about combining fleets from different countries, it's something that we've all been thinking about, particularly because of the contraction of the Japanese fleet, which we've mainly relied on, and the increase in the other nations' fleets. So my question is selectivity the same among those vessels, so that we can easily combine them, or do we have to actually standardize for selectivity, which means we'd have to do like Haikon's doing with a size-structured CPUE analysis to estimate selectivity differences among the fleets?
That's a good point, actually, and I think we had to be more careful about that, and we just check with the mean length composition, mean length, or over the different fleets, and not significantly different. So that is why we move forward. But that could be, as I mentioned in my presentation, we may be able to compare length composition itself by area, for example. And if the different fleet use mainly the different areas, and if there is different selectivity, that might be a big problem. So by area and also by clusters, I think we can make some comparison more systematically, so that the joint CPU work will be more convincing. So that might be, so we need to work more. And also we haven't done the spatial temporal modeling for the joint CPUE. So that's another issue. So thank you.
Yeah, I think that is something that should be followed up with the spatiotemporal models. I have in the past modeled size distributions as a function of location and year quarter and location as 5 degrees square, year quarter and fleet. And in all of those analyses, fleet comes way down as the lowest contributor to size variation. Yeah, but it's not a very sophisticated way of modeling it, but my gut feeling on the basis of that was that there are no major differences in selectivity between the fleets. But yeah, it should be followed up.
Okay, thanks, Simon. I think Carolina looked at some of that too. Not sure for what species, in really small spatial scales, and found fairly similar lengths between fleets if you made sure you matched up time and space. The other thing that is related to this is depth. And is there any selectivity difference among depths of fishing? So, I mean, the obvious one is the surface sets versus the deep sets. But I guess there's a big range of variety of that. And also, it's not just the depth, it's the environment that you're fishing in. So in different areas, you're fishing at different depths to get in the same environment. So I guess it's a little hard to tell, but does anyone have any information about selectivity by depth? Toshi was quick to answer it there, now he's not. Nicola, you had a question you want to ask?
Not a question, but a comment for the joint fisheries stuff. I think thinking back to the longline workshop that the IATTC hosted in 2019, I think, where there were several distant water fishing nations that came together and made presentations of their high resolution data. If I'm not mistaken, or I'm not making this up, I think there were some interesting, almost competitive or avoidance interactions between different fisheries, and that where you had, like, within a 10 by 20 block, if you actually looked at the 1 by 1s, you didn't have a ton of overlap in certain areas. And so I think that's a consideration that needs to be made. Is the reason to go to joint modeling is to try to account for the fact that some fleets are no longer fishing where they once were. But if you don't have enough overlap between different fisheries, it's going to be really tough to estimate, I guess, the relative effects between some of those fleets. So going back to Simon's original point is really look at your data.
Yeah, Simon, do you want to follow up?
Yeah, I mean, I guess those models, when we standardize them jointly, we're not doing it by fleet, we're doing it with individual vessel effects in there. So we've got a whole lot of individual vessels. Maybe there are some, and maybe there are some differences in the way they fish that mean that some have slightly different selectivity from the others. But if there are differences in catchability between vessels, but by modeling them as individual vessel effects, you account for those.
Yeah, Nicola?
I guess my thinking is the smaller the unit, you almost make it worse, because then, or you could make it worse just because you lose the individual vessels might not overlap as much either. I know I've got an example that's, kind of myopic in the grand scheme of things in the Hawaiian Islands, looking at reef fish, but you've got certain vessels that never fish in the same spots as others. And so how do you estimate that vessel effect without it being completely confounded with the underlying abundance that vessel fishes on? And so that's, I guess, you have to have something to bridge the gap between different effects that you're modeling.
Yeah, and it depends on the spatial scale of your model. And I guess on the one hand, we're normally dealing with 5-degree squares, which are very big. Whereas I guess in the Hawaiian Islands, you're modeling things at smaller scales. At the 5-degree square scale, it's much, there's a lot of overlap basically. And then when we go to using spatial smoothers and spatiotemporal smoothers, you can share information over space and time more generally, and you tend to, that was an issue with some work I did with CCSBT. We were getting lack of overlap and the model was failing to estimate some parameters because it was GLMs and just categorical variables. But when you went to smoothers, it was able to connect up the things which were close enough to have similarities between them. And so that's, I guess, using smoothers is a more powerful way of dealing with those issues.
Yeah, Toshi.
So returning to the selectivity issue for the joint CPU, if we only need to avoid the issue on the selectivity, idea is to use the size-based CPUE, which means we don't need to care about the selectivity if there are constant, almost constant selectivity within length categories. But that kind of the length-based CPUE, if the stock assessment receives such information, how they use that information is one of the issue. And also we need to use it, length composition data twice in the such length-based CPUE and also the stock assessment for the length composition data. So I have no good way to resolve in all the angles, but there might be some room for consideration of the length-based CPUE or jointly smoothing of the CPUE and also the length composition over the space at a future direction. Thank you.
Yeah, the length-specific CPUE would have a nation effect in it, and that nation effect would be your selectivity, right? So you're estimating it automatically in the model. Yeah. Okay, we should move on. Thanks everyone for that. And we're going to move on to the next topic, which is natural mortality, I think, yes. And Simon's going to give the keynote on that. And then Kai Lorenzen is going to give a comment, and he's going to be talking virtually. But that will be after the break.
Okay, so this talk is based on some work I did for the Indian Ocean Tuna Commission, looking at natural mortality for yellowfin tuna, and then kind of drawing some general conclusions from that for various RFMOs and other tuna species. So this is the paper that we wrote up, just describing the results, and then did some further work looking at Big Eye as well. So yeah, the background, there was the 2021 CAPAM meeting on estimating natural mortality for fish stock assessment in general. And then there was some, at the October Rome CAPAM good practices meeting, there were talks on good practices for natural mortality in general, so I've drawn on both of those. So what I've done in this talk here is to review natural mortality estimates across all oceans for a yellowfin tuna case study, looking at the methods used to estimate natural mortality and the natural mortality O drives applied in stock assessments. And then developing recommendations for assessments in general. So the various components of M used in many Tuna assessments. I'm mainly going to focus on the base level of M here, but also discuss this juvenile pattern that's usually used of declining natural mortality. Many assessments use an adjustment for female M, which is influential because it's increasing the natural mortality of the adults. And I'm going to discuss why it should be greatly reduced or removed altogether. Of course, natural mortality also has variation with time, season, and location, but these are rarely applied and really almost impossible to estimate in Tuna assessments. So I guess they're hypotheses, but they're not testable hypotheses, so we can't really address them. So looking at potential sources of information on natural mortality, you can have direct estimates based on catch curve approaches, but the issues with these are that they can be biased high if you don't have asymptotic fishery selectivity. Of course, there are the usual issues with the variable nature of recruitment and variable nature of the environment and sampling. There was an estimate for yellowfin tuna in the EPO in 1961, which was very influential, estimate of 0.8. But this was based on using data from a coastal bait boat fishery, which was dominated by small fish. And I'll talk about that a bit more later. There are mark recapture methods. There have been several applications to yellowfin tuna. There was John Hampton's influential paper in 2000. Tom Peetman and others updated that in 2022. There was some work based on the Indian Ocean Tuna Commission's tagging program, Bosque et al. In 2012 and Everson et al. In 2012. Now, the estimates from these experiments were quite different in different areas. The estimates were very high in the WCPO and very low in the Indian Ocean, probably reflecting the different nature of the tagging programs. And one of the problems with estimates from mark recapture methods is that these methods, when you're estimating natural mortality, require assumptions that for these tuna, for the ways tuna are tagged, the assumptions are quite unlikely. And when you're trying to estimate natural mortality, they can cause substantial bias when the assumptions are broken. So incomplete mixing is a particular problem. And there was a paper by, I think, Honig in mid-90s looking at the effect of incomplete mixing on natural mortality estimates, and it was a really strong influence on natural mortality estimates in tagging experiments. There's potential for further simulation work to improve this, but at the moment, given the current state of the way tuna are tagged and the way the recovery works, for example, not getting many tags back from longline fisheries, so you get very low reporting rates from the longline fisheries. It's very difficult to estimate natural mortality using these methods. Of course, I can't not talk about close kin, and I'd get in trouble from Rich and Sorrow if I didn't. So these CKMR assumptions are less likely to be broken because there's no tag loss, there's no release mortality, and there's 100% reporting rates. So mixing and stock structure may still cause difficulties, but they do provide good information, and this is probably the option with the best potential. Population modelling approaches, they combine information from age structure, mark recapture, and other sources. So this is potentially more reliable than the isolated methods, since the models account for factors like selectivity and movement. However, you still do get model misspecification and data conflict, which can bias your estimates of natural mortality as well as other parameters. It's kind of as difficult to estimate natural mortality in a tuna model as it is to estimate steepness. And then we come to the empirical estimates from meta-analyses. And I guess the favorite at the moment is this one based on maximum age. The observed relationship of Amax to natural mortality in multiple fish to lightly fish stocks. So there was the database compiled by Denatel in 2015, originally John Honig's work, and then updated by Denatel, and then Hamill and Cope last year published a paper where they reanalyzed the Denatel and came up with the estimate of M equals 5.4 over Amax, with CV of 0.44 or 0.31 if you're looking at the value that you want to use in your predictions. Of course, there are problems. Amax can be reduced by fishing pressure, and that's a difficulty with tuna because all of our tuna stocks, during the periods we've been aging them, have been pretty severely impacted by fishing pressure. But Amax is increased by refuges from fishing, by more intense sampling, and also by aging error. So you need to understand what's going on with all of those issues. There are also relationships with growth, KNL infinity, and reproductive parameters. These don't have such a natural link with Amax. I mean, it's pretty obvious why there's a relationship between Amax and natural mortality. But the relationships with these other parameters are more in the nature of hypotheses. And you would expect, whereas the Amax relationship, you wouldn't expect it to have any variation between taxonomic groups so much, whereas with these, you can see that there could be good reasons why there would be changes between freshwater fish, between tunas, between other species. So maybe not quite so useful. And we do find that empirical models have, looking at those relationships, have significantly higher CVs. Okay, so going back to yellowfin tuna in particular, history of what's actually been used in the stock assessments. So this analysis by Hennemeth et al. In the Eastern Pacific in 1961, Hennemeth used catch curves with yellowfin tuna age 2 to 4 to estimate a value of Z of 1.72 and F of 0.5, and concluded that natural mortality was between 0.6 and 1. And that's where the estimate of 0.8 came from. But as I said before, this data came from bait boat fisheries, which mainly catch small fish. And the fishery at the time was close to shore, where the fish are also smaller than they are further out. So it's pretty clear that Z is likely to be positively biased due to selectivity, and that the methods overall and the tools that were available in 1961 for analysing these kinds of things, the results likely to be unreliable. But this, I mean, I guess it's something about how we do stock assessments. We don't have much evidence. We haven't had much other evidence of what M is, and as a result, M of 0.8 has been used ever since. The WCPO and EPO stock assessments, and it was used in the Indian Ocean until 2008 when the tagging estimates started to come in, which were much lower. So these are the most recent natural mortality ogives in 4 different tuna RFMOs. So the EPO using this base value of 0.8 and assuming a much higher natural mortality for females based on the way there are fewer females at greater lengths, and they were assuming the same growth curve for males and females. And so the way to explain the loss of females from those larger lengths was due to higher natural mortality. And so that's where this curve came from. In the WCPO, we took, when I was involved in calculating this ogive here, and this ogive was based on combining males and females. It's a single sex model, so you need one ogive for both sexes, and this hump here reflects the loss of females from the population. And in 2020, Matt Vincent and Nicolas calculated some new options based on different otolith growth and modal progression growth, and came out with some slightly different options. In the Atlantic, they've gone with more of a Lorenzen curve approach, and this is the two most recent estimates. The 2008 without the decline for juveniles, and 2019 going with this more direct decline following the Lorenzen GLIM approach. And in the Indian Ocean up until 2018, following that approach with a hump for dying females, but also having lower base levels due to the information from tagging experiments and trying to fit those data inside the stock assessment. Okay, so this is where we got to in 2021. We had these most recent values of natural mortality, with the base level of natural mortality based on the AMAX, which is, I'm sorry, I'm pointing to the wrong one. So this was the basic value that we used. The line here is from the previous stock assessment in 2018, and the red line here was a value that was called the ICAT, based on information from the ICAT assessment in 2018. And this was an approach that the grey and the red shading were values based on another model that Mark and others had suggested, where you had a declining natural mortality early for juveniles and then an increasing natural mortality later on as fish matured. So this was a hypothesis that mature tuna had an increased rate of natural mortality. Then what we decided to do was to look at the values of M across all of the different RFMOs, all of the different areas, based on all of the different AMAX values for yellowfin. And in 2021, there was a study that got a very high value of maximum age of 18, which was really seen as surprising, because yellowfin tuna weren't considered to live that long. But they found 6 fish aged 17 to 18, which is a really strong result. Doesn't seem to be just aging error. And it implies a natural mortality of 0.3, which is a lot lower than the 0.8 that was being assumed in many places. And this was corroborated by a BOM radiocarbon study, and very little difference between males and females, with 18 for males and 17 for females. In the WCPO, the oldest fish was 15, implying 0.36, and the oldest female was 13. And the Indian Ocean, with actually not very much sampling, and most of the sampling in an area with a lot of fishing in the purse seine area, AMAX was basically 11, applying M of 0.49, and oldest female was about 10. Okay, so those were all suggesting much lower levels of natural mortality than the previous assumption of 0.8. Next issue, natural mortality by sex. That question of whether sex ratio varies, the variation of sex ratio with length in tunas is linked to natural mortality, or whether it's due to differential growth rate between the sexes. So past models have assumed that this variation in sex ratio at length, which I'm showing here, at greater lengths, it's quite substantially biased towards male sex ratio. So we assumed that this was due to higher female natural mortality, but now we know that males actually grow larger. And this difference can partly or wholly explain those changes in sex ratio at length. If you look at this plot on the lower right, the black, and this comes from the Indian Ocean, the black dots are the males, are the females, and the red triangles are the males, so showing significantly larger L infinity for males than for females. And based on this, you can infer that that hump in the ogive, which is based on higher natural mortality for females, it should be either much smaller or removed altogether. Another issue to think about with natural mortality for tunas is senescence. And in some stock assessments, they use senescence to, at the end of the, particularly I think for skipjack, they use senescence. And senescence is ubiquitous in animals, but it really hasn't been studied very much in fish. It is obviously a feature of semelparous fish like salmon, but it's not often seen and not often identified in iteroporous fish like tunas. There have been some studies in gobies where they have found senescence, but it's generally found at ages that are much, much older than any fish would survive in the population based on the rates of natural mortality that they observe in those populations. So the inference, I guess has generally been inferred from that is that because iteroporous fish continue to grow throughout life, there's no evolutionary pressure to evolve senescence, or at least there is evolutionary pressure to continue to survive long term because they're continuing to breed, they're getting larger, they're putting out more and more eggs as they get older, so why not keep living? Yeah, so again, there's just not that much evidence for senescence at reasonable ages for tunas. So possible approaches for natural mortality. One of the questions is, should we use for the Indian Ocean, should we use the local value of Amax to define natural mortality, or should we use the global value of Amax? Natural mortality does have extrinsic and intrinsic components. It can vary between stocks due to environment, predation, and disease, but also yellowfin tuna physiology, behaviour, and sex differences and senescence at age are likely very similar everywhere. And we also know that the degree of sampling and the amount of fishing pressure on the areas that we're sampling varies a lot between stocks. So on the one hand, we've got an estimate of 11 for the Indian Ocean. On the other hand, we know that yellowfin can live to 18 years old. So those are two possible hypotheses, and given the fishing pressure in the Indian Ocean, the option that we decided on the Indian Ocean was to propose using both 11 and 18 as alternative hypotheses. Next question is, how do we deal with natural mortality at age? And Kyla Ensign has proposed the generalized length inverse mortality paradigm with natural mortality declining in proportionate length. This is strongly supported by empirical meta-analyses. It's consistent with models of predation mortality. Deviations have been, like in the data, deviations have been found for fish species in older ages and early juveniles, but there's little evidence for increased mortality associated with maturation. So in terms of natural mortality at age, it's the most reasonable hypothesis is to assume that tunas follow that same declining curve of natural mortality at age as we see in other species. So the alternatives that we previously proposed for the Indian Ocean were these two different options, this declining option based on the Lorenzen-Glim curve, and this other option based on hypothesis that there was increasing natural mortality for for mature fish. And I think my preference is certainly to go for the first option with the declining over the entire life cycle. So we proposed these two alternative hypotheses of just showing here that the red line is what was used previously. These two values here, one based on Amax of 10.9 and one based on Amax of 18, and both using the Glim curve. And went through and applied that same approach to all of the different oceans. And they're really same shape, obviously. And all of these differences are simply based on the differences in the oldest fish in each ocean, and with the lowest value being the Atlantic with the 18-year-old fish. Also looked at the effect of applying this different natural mortality to the yellowfin stock assessment for the Indian Ocean. And it has quite a big impact, actually. When you have a lower natural mortality, you get lower productivity and you get change in the stock status, especially when you go with the Atlantic version. Applied the same approach to big-eyed tuna and came up with a set of natural mortality ogives. And in this case, for the Indian Ocean stock assessment, it has much less effect. I'm just going to go to the conclusion. So as a result of, after comparing these different approaches, we'd recommend the AMAX-based methods, with the Venedal approach being superseded by the Hamel and Cope approach of 5.4 over AMAX. Recommend using a global and local AMAX as alternatives, given that local AMAX can be affected by high local fishing mortality and limited sampling. And that's probably the case for most of our tuna stocks with relatively limited sampling and for age data and pretty high F values. Recommend using the Glim paradigm for M at age, and also this other point, using the average over the fully exploited age classes to represent the base value of natural mortality. And this approach is largely consistent with what's being done in ICAT. So Rome, they came up with a set of recommended good practices for natural mortality, and they were, I guess, fairly similar to these. I've gone through and looked at them and kind of ranked them for tunas. So the first one is to develop and use a prior or an associated point estimate for M based on life history correlates, with the preferred approach being Hamel and Cope with log scale uncertainty of 0.31. And to that I'd add using local and global AMAX as alternative hypotheses. Yeah, the default should be the not constant M, but using that size selective mortality, because that's well supported by the data, and there's really no reason to just go with constant M when you have that strong data support. Also, for a stock assessment, you need to recognise and explore uncertainty in M and thus in the assessment. So do things like modelling the different levels of complexity and alternative values of M by sex and age, and also use simulation and MSC to explore uncertainties. If possible, you can try to estimate M in the assessment with a prior, and consider what other parameters should be estimated at the same time, such as steepness. But as we've already discussed, there's a lot of model misspecification in our assessments, and you really can't trust the values that come out of these estimates. You can do all this reviewing of diagnostics, but I think in the end, you're just going to go back to your AMAX estimate. And these other two approaches, exploring M using multi-species models or considering adaptive effects, I think we've got a fair way to go before we can look at those, or at least use them in our assessments. So I think my time's up. Thanks.
Yeah, thanks, Simon. We got some time for some questions. Yeah, Pamela.
I'm not sure whether you know the answer to this, Simon, but just out of curiosity, how frequently is M estimated within models and Tuna stock assessments versus externally imposed on the model?
I think most of the time we impose it. Most stock assessments impose it. There are usually sensitivity analyses that are run looking at estimating M. And I think that probably happened more in the past where people tried to estimate M in stock assessments, but in recent years, I think people have moved more towards fixing natural mortality.
And then I guess a related question is estimating different M's over time or trends in M over time. Do you have any examples of where that's been done?
Maybe others could. There have been some recent papers. There was a few papers in a special issue on natural mortality, which looked at using random effect models to estimate natural mortality. I can't remember the name of the guy who did that, but yeah, I think I'm pretty sure it has been done.
Yeah, especially those state-based models are now estimating M because it's part of the state-based thing. But I think, can't remember his name, from Canada, yeah, did it. Okay. Yeah, sorry. There are some sort of research papers that have done it. I don't know about actual ones that have been used for management. Any other comments or questions for Simon? Yeah.
I think natural mortality is also quite related to some kind of like immigration and emigration. So especially when you focus on some local stuff, like how do you incorporate that kind of impact? I guess like the simplest way is to allow natural mortality to be negative, to allow some kind of immigration from the other areas. And is there any other approaches that you can recommend?
Yeah, I guess in a stock assessment where if you're not estimating it, then you're just imposing a value of natural mortality, so you don't have to worry about the immigration issue. Maybe.
Yeah, so in fishery stock assessments, we tend to define our population as sort of a closed population. And so we don't really have that confounding. Whether or not that's true in actuality or not is another thing. In wildlife stocks, with the market recapture stuff, they usually have an open population, and so the estimates of survival are basically apparent survival, which include values for immigration, and then often they'll estimate the immigration as another process. So, but something worth considering in stock assessments, because we generally just assume that it's closed, and so we don't worry about any confounding factors between immigration and natural mortality.
Yeah, I had a question. Laura had a question.
So yeah, I think we might. Carolina, might as well.
Simon, you're saying that we should have the same vector for natural mortality, right, for males and females. Then we will have to explain the difference with growth, right? So should we then have sex-specific data just to corroborate that we are getting those ratios correctly? And I think at least our assessment is sex-specific, but I don't know about the rest of the assessments.
Yeah, I don't think the other assessments are sex-specific. It would certainly be useful to have sex-specific data to be able to estimate those patterns in sex ratio at length, which tend to vary spatially and seasonally as well. So it's quite difficult to get enough well-stratified data to estimate those, to estimate how much growth difference there is and how much, basically I think you'd have to estimate growth curves first, and it's much easier to estimate length at age from otolith sampling than it is from looking at sex ratio at length distributions.
Okay, so I think we'll close for coffee, and after that we'll come with Kai's presentation, which probably will be talking about some of those aspects, and then we can bring it up again in the discussion section afterwards. But if natural mortality is related to K and growth differs between males and females, does natural mortality different too, and selectivity and lots of other things. Okay, back at 3:30, I guess.